Welcome to the new era of industrial storage rack design. For decades, the material handling industry relied on a mix of generalized rules of thumb and conservative estimates. Today, the landscape is shifting from outdated assumptions to precise, engineered solutions. At the center of this shift is the 2025 California Building Code's adoption of ASCE 16.1-2023 and the metric known as Kconn, the rotational stiffness of beam-to-column connections. Today, we'll explore exactly what this change means for your warehouse, your liability, and your bottom line. The regulatory foundation has been updated. The 2025 California Building Code now requires industrial steel storage racks to be designed in accordance with ASCE 16.1-2023. A critical update in this standard is the explicit evaluation of Kconn, the rotational stiffness of the beam-to-column connections. Connection testing, or proper calculation, is no longer optional best practice under the ASCE standard. It is the accepted method for demonstrating compliance. To see how this is being applied locally, look at the City of Fresno's current Storage Racks Plans Submittal Guidelines and Requirements document, dated April 2, 2026. For any rack system over 8 feet in height or with a height-to-depth ratio greater than 8, the city requires a building permit, a complete layout plan, seismic anchorage details, and structural plans and calculations prepared by a California licensed engineer. These designs must comply with the 2025 CBC ASCE 7-22 and ASCE 16.1-2023. The chain is clear. The code now points directly to the 2023 RMI standard. This update moves the industry past what we call the assumption trap. Historically, rack connections were often approved using generic load tables or blanket-safe assumptions. That created friction on both sides, owners asking why extra testing costs were needed, and building officials seeking reliable ways to verify stability in high-seismic zones. The updated standard bridges this gap. Physical connection testing, or accurate calculation, does not assume structural behavior, it reveals it. By establishing this factual baseline, the code protects public safety while safeguarding your capital investment. Unlike traditional buildings with extensive cross-bracing, the down-aisle stability of a pallet rack relies almost entirely on its beam-to-column connections. These joints are semi-rigid. They provide a specific partial resistance to rotation. If we do not know exactly where a connection sits on the stiffness spectrum, the structural stability of the entire frame cannot be accurately calculated. Without tested or calculated data, engineers are forced into guesswork that leads to two extremes. Overestimating flexibility results in unnecessarily heavy steel, redundant bracing, and higher project costs. Overestimating stiffness creates a sleek-looking design that may experience excessive sway and fail to meet seismic drift limits. Either path is risky. That is why ASCE 16.1-2023 introduces Kconn as the ultimate metric. Kconn is the measured or calculated secant stiffness at exactly 80% of the connection's ultimate moment capacity. This precise value captures the connection's true behavior near its structural limit and gives engineers a consistent, code-approved parameter they can trust. We obtain this value through rigorous cyclic testing in the laboratory. A beam-to-column assembly is subjected to alternating clockwise and counterclockwise moments. This simulates real-world dynamic loads and seismic events. From the resulting data, we extract the exact rotational stiffness needed for safe, compliant design. This is a major leap forward in accuracy. Older methods used a linearized spring constant and applied a harsh 2/3 reduction factor to compensate for uncertainty. The modern Kconn metric measures stiffness exactly where it matters, allowing engineers to use the value directly in their models. No arbitrary reductions required. The 2023 revision of ASCE 16.1 made another important correction. It shifted from static point averaging of left and right moment strengths to cyclic slope verification, averaging the full directional behavior across both clockwise and counterclockwise rotations. This ensures Kconn reflects the connection's actual, real-world performance and prevents dangerous overestimation of frame capacity. Once Kconn is established, engineers use it directly in the direct analysis method. Accurate connection stiffness lets them properly predict P-delta effects, the secondary bending forces that grow when a rack sways during an earthquake. In seismic zones, this exact data can be the difference between a rack that survives and one that follows a collapse trajectory. For warehouse owners, the cost of connection testing or proper calculation is a high return investment. It eliminates overly conservative guesswork, often allowing leaner, optimized steel designs that save money on material and installation while delivering full code compliance and future-proofing the asset. The 2025 code update also levels the playing field for safety. Building officials can now consistently require designs that follow ANSI MH 16.1-2023. Engineers of record who embrace the standard protect themselves from liability, while owners receive safer, more efficient racks. We are entering a new era of material handling engineering, one defined by evidence, not assumption. Kconn is a code-supported parameter that unlocks safer, leaner, and perfectly optimized warehouse structures. Compliance is no longer about arbitrary safety factors. It is about leveraging actual structural behavior to protect lives and investments. By partnering with accredited testing labs and using the Kconn metric, the industry is building a safer, more resilient future. Remember, testing does not assume behavior, it reveals it.
The most efficient path to compliance is a collaborative one. Warehouse owners should partner with manufacturers who provide empirical Kconn data as a standard specification. This evidence-based approach streamlines the permitting process, eliminates project-level sticker shock, and ensures that every system, especially in high seismic zones, is built on a foundation of verified structural behavior.